Okay, so he knows what I'm talking about. Turns out this is Alexander Lovique. He is a researcher in artificial intelligence. He has a Google Scholar page, all of 108 citations. So it's bad enough that I'll be missing a lot of classes to go give lectures in other places. Now I also have to go to fashion shows, I'm pretty sure. So I guess AI hype has officially jumped the shark. So that's the latest, this last latest story. Anyway, so what we are going to be doing first is to try to get you to remember all the things that we learned about A-star search, and then basically we will go from there. Okay, so let's just go through this quiz one by one. Okay, so the first one, breadth-first search is a special case of uniform class search where the edge operator cars are all equal. I am going to talk to what? Oh, you want to see the okay. So that's 91% of you thought that that's true, that is breadth-first search is a special case of uniform class search where the edge and operator class are all equal. So that is indeed the case. In fact, the strange thing is the word uniform class search is used to talk about the case where the edge class are non-uniform. Okay, it's almost sort of, sadistic to name things in such silly ways, but that's the way it is. It's been just called uniform class search. The uniform there doesn't mean that all the edges have the same cost. It actually means that the edges have very, very different costs. Okay, and breadth-first search basically breadth-first search assumes that the cost of the solution is just its depth. What that means is that if there are two solutions at the same search depth, then they are both considered to be of equal cost. Okay, and so you can get that behavior by essentially assuming that all the edge costs are equal. Normally people just assume unit cost, but it doesn't really have to be unit cost. It can be, as long as all those are equal, then you get the same exact behavior. Okay, let's look at the second question. And I'm going to finish this. Start the second one. Uniform class search is a special case of A-star search where H of n equal to G of n. Remember that A-star search has H values. So this is the one that we're looking at. Uniform class search is a special case of A-star search where H of n equal to G of n. Okay, we have 106 people already voted. I'm going to stop. Okay, so I'm just saying here, uniform class search is a special case of A-star search which H of n equal to G of n. Okay. So most of the majority thought it's false. The minority, 1/3 of you thought that's actually true. So somebody who said, in fact, but that in fact it is true that to get uniform cost search by plugging G of n, H of n equal to G of n in A star search. Can one of you explain what your thinking was? Yes, it was just a random selection. How about this? Somebody who thought that's false. Yes. Yes. Okay. By the way, just to make it clear, I will try to look for diversity of answers. So if you're one of the people who does have an answer, please raise your hand. But I may choose not to call you if, in fact, I pretty much can tell that you have spoken in a few times and I know how you are. Okay. So it's not any discrimination. I just want to hear all the voices. Yes.
So for G of n is the cost to get to that node so far is the basis by which we choose which node to extend next from cost search. But H of n isn't the cost to a node, it's an extrapolation of how much we have left to go, which really is comparable to the way it's used in A star search with G of n in cost search.
Okay. Did anybody have any questions on that answer? Anybody who wants to say why they thought it is true, please speak up, because your life doesn't. It's good to have your misunderstandings clear. Yes.
In your respect, we don't know in uniform courses we don't know what the distance is left between the core and our current node. But in we assume that how far they are from and how far they are from.
Yeah.
So in uniform core search, we just know how far they are from.
Yes.
So that's why H is kind of.
No, so the point is, whatever you said and your conclusion are unfortunately disconnected. Basically, because let me write on this. Okay. So you have root node and you are at this node n, and then somewhere here is goal node. Oh, okay. Yeah, this is not, this takes too long. Okay, so you have root node there, and then there's a node n, and then there is goal node g, right? So this is n. And probably I should call this capital G here. Okay, and this is h of n. H of n is cost to go. This is being aware of how far. So first of all, unless you have memory problems, everybody is supposed to know how far they have come. Do you understand what I'm saying? You can choose not to use your brains, in which case, of course, you have no clue how far you have come. But knowing how far you have left to go is a higher sign of intelligence, because in some sense you are thinking about how long, how much more distance do I think I have to go. For that, it's actually important to have some understanding of the total distance to begin with. Okay, so H of n essentially is cost to go, and that's the informed part of the informed search. Okay, uninformed search is not clueless search. Even uninformed search keeps track of how far it has traveled. You can have clueless search, which basically has no clue where it has gone. Okay, but so G of n is keeping track of how far you have traveled. H of n is guessing how much more you have to travel. In fact, the idea that you want to keep in mind is the best way of estimating H of n. No, the first thing that should come to you is there is this question. Actually, somebody asked about Einstein about research, and Einstein said, if I know where I'm going, it won't be called research. Okay, to some extent, knowing where you are going to go makes the problem less interesting. Okay, so in fact, you might ask, how would I know H of n unless I do a search from here until the goal node? The best way of figuring out H of n completely is to start from here, do the search until you find the optimal path to the closest goal node. that would not be an estimate really, it would be the perfect heuristic, it would be H star of n. Okay? You could do that, but you're not going to be impressing anybody, because if you were to do that, in a sense, the search would be, the overall search would, expand the fewest number of nodes, but you spent all your time computing this highly accurate value of heuristic. And one of the things that I hope you got, and if you didn't, it should become clearer in today's class, is how do I get an estimate of how far I have to go without having completed the problem. It looks as if you're trying to get something out of nothing. And the normal way you do it, and it becomes, I'll repeat it many, many times, is you sort of simplify the problem. You abstract the problem out. And then say, if I know approximately, if there's a fast way of solving the approximate problem, and as long as the problem, the new problem is an abstraction. Abstraction means it removes constraints. It doesn't add new constraints. It removes constraints. Okay? As long as that is the case, then basically the estimate you got by solving the problem exactly in the abstract case, so solving the problem exactly in the abstract case becomes an optimistic estimate for the original case. So an example is, if I need to decide how to go to John, who's sitting way back there, I want to hit him on the head, I'm basically trying to find the path. Okay, I'm right here, how do I find the path? I have to probably walk around, not basically disturbing the camera, etc., and go there. The exact distance depends on, all the obstacles that are out there. Maybe, in that alleyway there, somebody put a, laptop, and so I shouldn't step on it. Right? I don't know until I get there. You see what I'm saying? So I don't know the exact distance I have to go to John. Okay. However, I can abstract this out. I'll say, boom, everybody is disappeared. There are no chairs here, no people here. Only John right at that point. At which point it basically is a planar problem where he's a point on the plane and I'm a point on the plane. And it turns out that we know how to compute the distance between 2 points on a plane. You don't need to do search. So you just take Euclidean distance between me and John. And that is an optimistic estimate of the distance that I would have to travel if I actually travel in the real world of this class. Do you see what I'm saying? Okay, so I basically abstracted it out by essentially removing all the constraints. I said all the chairs have gone away, all the people have gone away, except thankfully John. If John also is gone away, then the distance would be infinite. Okay, now a variation of, so of course abstract problem here is actually easier to solve because I just had to compute the distance between 2 points, and we know what is the optimal distance between 2 points on a plane because Euclid told us that. Okay. How about if all I care about is making the problem easy to solve? I have a different way of making the problem easy to solve. I'll close my eyes and assume there is no way I can walk. Basically, there is a huge wall, around, John. You see what I'm saying? At which point, too, I can very quickly answer the question of how much of a distance I have to John. Infinite. But that is a pessimistic estimate. It's not an abstraction of the problem. I added more constraints than were there in the original problem. You want to understand this distinction. An abstraction is only basically removing constraints. And if you solve the problem exactly in the abstraction, then you get that length, that heuristic cost would be an admissible heuristic for the original problem. Okay, we talked about admissibility. You heard about admissibility. Okay, next is an admissible heuristic H should have the property that h of n is equal to 0 for at least some nodes assuming that there are goals in the word. So I'm going to restart again. Okay, so I'm basically saying that if I'm thinking of an admissible heuristic, if your friend gave you an admissible heuristic for a problem, which does have goal nodes, and it turns out that you looked at this h of n function, and it's not zero anywhere. The question is, can such an admissible function, such a heuristic be admissible or not? That's the question. See, the advantage of asking this here is if I get these things out of my system now, they won't be on the exam. Right? Okay. I'm going to stop this and show you what they said. Okay. So again, 2/3 said true. It seems to me that there is a 2/3, 1/3 distinction. Some people are actually sleeping as I speak, and I'm saying this loud so that maybe they might hear it through the depths of their sleep. But by the way, little later during the semester, I'll start throwing some sort of things on people who are sleeping. So that's a good way of saying. I'm trying my best not to look at the people who are sleeping right now, just not to look at them. But, okay, so basically the question is if you have a goal node, can you have an admissible heuristic which is not zero anyway? Okay? And most of you seem to think it has to be zero somewhere. Right? That's the way I wrote it. Admissible heuristic H should have a property that h of n equals 0 for at least some nodes. Okay. So, can somebody tell me, somebody who thought that is true, can somebody, yes, go ahead.
So what I was looking at for an admissible heuristic, h of n must always be less than h of n star.
Okay.
And so if h of n star were at any point, if h of n star,
H star of n.
yeah, h star of n. So if h of n were 0, that means that since it's less than or equal to h star of n is equal to 0 as well, because that's the only value it can have.
Yeah, that's.
And that would happen at the goal. So as long as there is a goal in the problem, there's a place where it can be less than it. It's when they're both 0.
Okay. Did people understand? Yes, what are you going to say?
I answered true. Can our heuristics be negative?
No, they are costs. They're not negative. Okay. It's basically it's cost to go, so they cannot be negative. Okay, so the thing basically that this gentleman is saying essentially is the most important thing I want you to remember from that is admissibility is a for all property. Admissibility is a for all property. For every node, for every search node, the true cost of going from that search node to the closest goal node should be higher than what the heuristic is saying, higher or equal to what the heuristic is saying. It's not enough that a few of the nodes have the right property, the rest I don't care. Do you understand what I'm saying? And so if you can find at least one node, even one node where the admissibility property doesn't hold for that node, then the heuristic is not considered admissible. You can't say, look, I'm admissible, quote unquote, for 99.99999% of the nodes. Why do you care about one node where I actually happen to be, not actually a lower bound? You have to be a lower bound at every node for you to be called admissible. Do you understand what I'm saying? And once you understand that, then you realize that if there is a goal, then it's obvious that the true cost of going from a goal node to itself, unless you're completely curious, is 0. So every estimate has to be less than or equal to 0, and these are distances, and so they have to be positive, so they have to be equal. That's a more interesting, complex way of understanding it. This makes you realize that heuristic is a for all property. And a second order point about this is that if the heuristic is admissible, you are guaranteed that A star search using such a heuristic will find an optimal path. But if the heuristic is not admissible, it does not mean that A star won't find optimal path. But you would not know whether it found optimal path or not. And the thing that you want to understand is optimality is one of those things that it is completely useless to tell, well, I'm sometimes optimal. How the heck do I know whether you are optimal on this particular problem or not? You know, if you say I'm sometimes optimal, then how to, basically on this problem, to check whether or not you are optimal, I have to do the entire search myself. Do you see what I'm saying? So saying I'm sometimes optimal is like basically useless. Okay? And so in fact admissibility is a sufficient condition for optimality of the. There can be situations where you might have a heuristic that's not admissible, in the sense in some nodes it's actually violating this lower boundness. And yet A star search, that you run that A star search, and you find the optimal path because you happen to know the optimal path for this problem, and you find your search did find it. And you would say, wow, there's something wrong. Admissibility theory is good. No, admissibility theory still is right. If you have that property, you didn't have to double check. Do you understand what I'm saying? Okay, a guarantee should be, you don't have to double check. If I have to double check, it's not a guarantee. So imagine, what is honor code? Honor code is a guarantee that you will all play by the rules. Let's say, we are mostly honorable. Then we are all screwed because the TAs and I have to keep on checking whether you are cheating on this particular exam or that particular question or something else. Do you understand what I'm saying? So if you all agree to the honor code up front, then that's a guarantee. Then I don't need to waste my time. And I can spend time teaching as against checking whether you cheated or not. So similarly, optimality, you need a guarantee up front. You can't just say sometimes I might be optimal. I might just by fluke be optimal. Even if you say I'm 99.999999% of the time I'm going to be optimal, that's still no guarantee that the current problem you happen to be optimal. The only way I can check whether or not you're optimal is doing all your work again. And you want to write this down somewhere, that unlike, there are two properties of a solution, okay, for any problem. One is correctness. Is the solution correct? The other is optimality. Is the solution optimal? You want to write down somewhere and keep remembering that correctness is a local property. Irrespective of how I came up with the solution, if I gave you the solution and say it's correct, you should be able to check it without having to spend as much time as I did coming up with the solution. In fact, those of you who may have heard of NP completeness in any theory course, you realize essentially the class NP is all the problems where if somebody were to give you the solution, you can check if it is a solution or not in polynomial type. But finding that solution can be exponentially hard. In general, you assume verification of correctness is going to be cheaper than producing that solution. On the other hand, optimality is not like that. If I give you a solution and say, I think I'm optimal, you have to do all the work I did, probably plus more, to check whether I'm actually optimal or not. Optimality is a global property because whether or not a solution is optimal depends on what other solutions are there in the space. Correctness is a local property. Whether or not this solution is correct just depends on this solution. It's extremely important, bigger point that comes across in lots and lots of places. This is why optimality, you want to give guarantees upfront, not, sort of be wishy-washy and say, I think it kind of maybe optimal. That's not good. Okay. Okay. The next one is, of course, the next one. If H1 and H2n are both admissible, then H1n plus H2n will also be admissible. Again, it's very much, if you were at the lectures, you should know the answer. If not, then it's kind of an interesting question. But since it's time for us to take attendance, what I'm going to do is to convert this into a short answer question. Okay, either right, true, or false, or yes or no. Okay, that's your attendance. Okay, start this. Okay, so even if no answer, say something because this is also attendance. We will actually, if you didn't type anything, then you are not present in the class. Maybe you are asleep. Okay. You want to stop this? I actually don't know who said what. This is just an attendance thing, so let's go back to. Okay. So, how many people? Sorry. So, how many people said yes to this? Raise your hands. Okay, how many people said no to this? Raise your hands. Okay. Anyway, so I'm chuckling because I'm reminded of a Seinfeld episode where Kramer tries to be the guy who answers what are the films playing in a movie theater by pressing the buttons, and then he obviously can't sense that, so he asks to talk to him. But anyway, that's a long story. But so the majority basically said H1 plus H2 cannot be admissible. It's not guaranteed to be admissible. That's basically because when a heuristic could be admissible in, for example, by being equal to the correct value at some node, equal to the optimal value at some node. And if you add even an epsilon to that, it will become inadmissible then. Do you see what I'm saying? So in general, if you have two heuristics, H1 and H2, adding them up doesn't give you an admissible heuristic. A dream of this area is the following. The reason you actually have two heuristics is often because there are two very different ways of abstracting the problem. Each abstraction gives you a different heuristic. And it would be very nice indeed if both heuristics are admissible because they are both abstractions. So it would be very nice indeed if in fact the sum of the heuristics is also admissible. Okay, now why is that the case? Here is a different question I'm going to ask. Forget about admissibility. Imagine there is an A-star search that is searching the world with H1n, searching the tree with H1n. Another one is searching it with H2n. So you get to, so basically the three cases, A-star search can search the tree either with H1n or H2n or H1 plus H2n. Which one do you think will do fewer node expansions? Which one do you think will do fewer node expansions? No, forget about admissibility aspect. Yes, I'm giving you two heuristics. It doesn't matter what those heuristics are. Okay, I decided to add them up in the search. Would I do fewer expansions or more expansions, or you can't say anything. More often than not, the bigger the heuristic value, the fewer expansions you will wind up doing. That's why you actually define this notion of informedness, even though the notion of informedness is qualified on the heuristic actually being admissible. But it's actually, informedness is going to be correlated with the number of nodes expanded. And the bigger the heuristic, the faster the search will get done. Now, if you have any question as to why this is the case, optimism versus pessimism. Optimists think everything is going to work out. Pessimists think nothing is going to work out, it's all going to end tomorrow. Whose life is going to be quote unquote easy in terms of the amount of effort spent? If you're going to say that the world is going to end tomorrow, you will end it all yourself. And so you're done very fast. Okay, optimists on the other hand can be cluelessly optimistic. They might be actually, in fact, the world is in fact going to end tomorrow, but you think, that's all completely fine and everything is going to be fine. So you're saying h equal to 0. Because h is cost to go. When you assume cost to go is high, you are being pessimistic. When you assume cost to go is low, you're being optimistic. Okay, pessimism is a good way of actually doing less work. Imagine I give you a project, project 1. Some of you are very optimistic, it can be done, it can be done, it can be done. Some of you are really pessimistic, oh my God, this is way beyond my capabilities. Who gets done with the assignment fast? Being done with the assignment is saying, I'm done, that's it. There are always people when we give exams, there are people who walk out in the very beginning of the exam. They could either be the geniuses of the class, or they have h of n equal to infinity. You see what I'm saying? This is Rao's exam, why am I wasting my time? Let me go home. At least I can have some good sleep. They got done much faster. And they could actually say, imagine it is indeed Rao's exam and it is torturous. And the people who hung around for the 3.5 hours probably didn't do any better than this guy. And this guy got done faster. You see what I'm saying? So h of n being larger quantity